and now I can go back into, where's our game plan we had from the start. Here we are, okay? Can go back to this, because check it out. I know that 90% has to be equal to the H1 that we had from the start when we looked at the superheated table, right? So that's a 3399. So 3399.5 minus enthalpy 2A, which I don't know, which is what I'm after actually, right? And then divided by the same thing, 3399.5 minus the number we just found, 268. Okay? So note that the only unknown that I have here is that of the 2HA. Okay, so what I can do is obviously take this subtraction here, multiply that by 19, that has to be equal to this, and then I just need to do this guy here minus whatever I found, and that's going to give you my 2 H2A, right, the actual one. So because this is the only unknown, I end up finding that this guy is, what did I get? 2,381 kilojoules per kilogram. Okay, now I have two pieces of information that are crucial. I know the entropy of state 2A, and I also know the pressure, right? So now I can say, okay, so now state 2A, and remember that I use A for actual, right, to say that this is the actual state, not the ideal one. It has a pressure of 30 kilopascals that we knew from the start, and has an enthalpy of the number we just found, 2381.6. Okay, so now that I have those two pieces of information, I can go back to my pressure table, and I can check whether this is superheated, saturated mixture, all those things. Yeah, we don't expect it to be superheated for obvious reasons, but we always need to be sure, right? We need to be sure. So again, obviously, we already have the highlighted 30 kilopascals because we were using this for the ideal case. Let me go ahead and remove some of this. Okay. And I'm going to be concentrating here on the enthalpy one. Let me get rid of this, because I want to ask myself the same question. Is it between these two guys here or not, right? So is my number, the one that we just found, to be 2381 between these guys? It is, right? 2381 falls between these two. So I can be sure this is a saturated mixture. Okay, I can be sure that's a saturated mixture. And, right, the last piece of the puzzle is, if this is a saturated mixture, then this has to be at the saturation temperature, which is 69.09 degrees Celsius. Okay, so that's the jump that we need to do. Okay, if, right, and because we know that this number, the enthalpy number, falls between these two guys, then I can be sure this is a saturated mixture, and therefore, right, therefore I can do the jump here and say, okay, so therefore the temperature is 69.09. So that's answer of part 1, or part A, right there. And the last piece of the puzzle is, okay, but what is the output of this guy, right? What is the output? And we know that too, because we know all the pieces, information we can possibly get out of this problem. We know we now have this all sorted. We have this all sorted. So I can go ahead and say, okay, if I want to find out what is the work, if I want to find what is the work, I can just do the H1, which I always knew to be 3399.5, minus the actual one, which I found out to be 26, I keep saying 26, 81.6. And note that this is kilojoules per kilograms. And if I multiply that by my 3 kilograms per second, what I'll be left with as my kilograms and kilograms go away is kilojoules per second, which is kilowatts, right? So this guy turns out to be 3053.7, 3053.7 kilowatts, right? The answer that we saw in the beginning is already in kilowatts. I would probably go ahead and do this in as 3.05 megawatts. Okay, either way, obviously, same thing, your call. That's the answer, part 2. All right, so I'm going to ask you to go ahead and check whether this is true, right? So go ahead and calculate the power of the turbine considering the ideal enthalpy, and then obviously accounting for the fact that it's only 90% isentropic efficiency, and you should obviously get the same answer. All right, so not a simple problem because we're getting, a lot of information from the past. We're using every single thing we've learned in the previous weeks, and we're also now adding the idea of isentropic efficiency. Yet at the same time, if you have the fundamentals in place, you probably won't have any problem solving these kind of problems, right? If you have any questions, as per usual, just leave them down below in the comment section. If this video has helped you out, consider giving it a like, and we'll talk soon.